ask if everybody agree for the recording. So,
Yeah, I just asked.
François?
Oui.
You sent me a couple of days. I think you sent me all the documents that we have to fill, but I'm not able to.
Oui, je t'entends. Ouais. Tu veux que je te les renvoie?
Ouais, s'il te plaît, j'arrive pas à les retrouver.
Ok, je te renvoie le PDF.
Merci. Il y avait les documents à remplir.
C'est le. Oui, c'est bien YouTube qui fait de l'écho. Ouais, c'est bien YouTube. On n'avait pas essayé avec YouTube.
Yeah, so it's 2 o'clock. Do you think that we can start? Or do you want to wait for a couple of minutes?
Yeah, I think it's 2 o'clock, so we can start. We can start. Okay.
Okay, so good afternoon to all. So we are meeting this afternoon for the defense, for your defense, and how Chen, for the defense of your PhD thesis. It's a thesis you prepared at INRIA Sophia Antipolis under the supervision of François Brémond, and the PhD was also co-advised by Benoît Legadec. As most of you know, the defense will take place in 4 steps. So first, Hao Chen, you are invited to present your work in about 45 minutes. Then in second time, the jury will ask questions to you, and we'll have exchange around your work. Then in the third step, the jury will isolate itself to deliberate and write a defense report. And finally, we will deliver our deliberations to the candidate and to the audience. I've been appointed to be the president of this jury. And so myself, I forgot to introduce myself. I'm Frédéric Jury from the University of Caen, where I am a professor of computer science and specialized in computer vision and machine learning. And the other members of the jury are, so we have on the one hand 2 rapporteurs, we say in French, reviewers who have written a report about your work. So the first one is Vittorio Murino, who is full professor in computer science at the University of Verona. And he was formerly the head of the Pavis department. So Professor Vittorio Murino is a very well-established researcher. He's known worldwide for his work on computer vision, including person identification, action recognition, and many other topics. The second reviewer is, I'm sorry if I do not say it correctly, Xiliang Zhang, who is associate professor, and he's currently leading the Media and Vision Computer Group at the Institute of Digital Media in Beijing University. And he is well known for his work on person re-identification and fine-grained classification or image search. And other members of the jury are Rémi Munoz, who is a research director at INRIA Lille, and he is currently at Google DeepMind. I don't think it's necessary to explain what DeepMind is. And Rémi Munoz is also a world-class researcher in reinforcement learning, representation learning, and more fundamental questions related to machine learning. And we finally have the two advisors in the committee, François Brémond, who is a research director at INRIA Sophia Antipolis. He's currently the head of the STAR team that he created a couple of years ago. I think it was maybe 10 years ago. And he's developing generic system for dynamic scene interpretation. And Benoît Le Gadec, I know him less, so I believe that he's affiliated with a company named European Systems Integration, which is providing solutions for the security industry. So correct me if I'm wrong. Okay, so after this introduction, I think it's your turn, Hao Chen, to present your work, and then we'll be back in 45 minutes to ask you questions.
So thanks for your introduction, Pitik. So I will share my screen now. So you can see my screen? Okay.
Yes.
Okay, thank you. So first of all, thank you everyone for attending my PhD defense. So let me introduce myself first. I'm Hao Chen. I'm currently working for a PhD degree under the supervision of François Brémond here from INRIA Sophia Antipolis and Benoît Le Gadec from the ESI company. So also very glad to share my experience on person identification with my jury members and all the audience in the room. So I will give my talk on towards unsupervised person identification. So here, this is an outline for my PhD thesis. So I have made some contribution on person ID from supervised one to unsupervised domain adaptation person ID and unsupervised. Recently, I'm working on unsupervised lifelong person ID. In this presentation, I will first give a brief introduction to what is person ID and some major approach to do unsupervised learning, unsupervised representation learning. And then at the end, I will give some conclusion for this presentation and also some perspective for my future work. Even though I'd like to share all of my contribution with you, but due to time constraint, I only have 45 minutes. So I will mainly focus on the recent ones. So here, in this presentation, I will mainly talk about our recent work on unsupervised person ID. So I will talk about these three contributions. So let's start with introduction. First of all, what is person ID? Technically, if you have a network of a camera like this one, you can use a detection algorithm to tell you, okay, there is a person. But if you want to find the location of a specific person or to try to match a person of interest across non-overlapping cameras, in this case, you have to use your person identification algorithm that match a person of interest across non-overlap cameras. So basically you give a query image and we measure the similarity of all the image representations that captured by all the cameras. So here we can see we found the corresponding person in the camera 1. So since our objective for person ID is to classify the identity or to know the identity of this person, why can't we directly use image classification or image retrieval algorithm? Because we think for generic image classification task, for example, we have a very well-known benchmark, ImageNet. Inside this benchmark, we can have very big classes such as dog, such as human or tiger, or some vegetable. But for person ID, you have to enter into the class of human, and your objective is to try to distinguish different persons, mainly under the setting of non-overlapping cameras. So we can see person ID can be defined as a fine-grained image retrieval task. Since person ID is a very fine-grained task, so there are a lot of real-world challenges that can influence the performance of our person ID algorithm, such as a camera viewpoint, such as a person pose, occlusion, imperfect bounding box, low resolution, illumination conditions, and domain gap. We also can consider, in this case, for all these challenges, it can be considered on the supervised and unsupervised setting. But if you want to minimize your supervision in your person ID process, you have also to consider insufficient annotation situation. Among all these challenges, we are particularly interested in domain gap and insufficient annotation, which can make our person ID system more scalable and more adaptable. So here, we will mainly talk about these two. So first, what are the challenges in the cross-domain situations? We can see the situation is our person ID can be sensitive to domain gaps such as different illumination conditions, camera properties, and backgrounds between different data sets or different domains. If we want to have a very robust or reliable person ID system, we hope it can work under different data sets or different domains. But the real situation is if we only train on a certain training domain, such as the market, this data set, we can easily get a very high performance, such as 85% MAP, mean average precision. But if we don't do anything, we just test it on another data set, like this one, you can see there's a very different closest style. On this Duke MTMC dataset, we can only achieve like 25% MAP. So here comes our problem. So we can say our person ID system can be hard to generalize. So to achieve to adapt your model to a target domain, or to make your model more reliable or more generalizable. So we can do unsupervised learning on the target domain. So you can see we collect some directly collect some data from the second domain or the target domain. With all this unlabeled data, we retrain our model. But for this unsupervised method, we have some categories, some settings. First of all, it's a very traditional way to do this one. It's called unsupervised domain adaptation, UDA. So which means you can have a labeled source domain. You first train your model on the source domain, and then you use the unlabeled data from D to the target domain to adapt or to transfer into the target. And the second one is you can consider, because if you can directly learn knowledge from unlabeled data in the target domain, so in this case, you will have more scalability or more flexibility. This one is more related to a more recent popular self-supervised learning. So you don't consider any source domain, you just directly train your model in D2. And more recently, we also have another setting, it's called lifelong adaptation. So in this case, we can have incrementally added domain or incrementally added data. So your objective becomes to continuously adapt to new domains, but we want to have a model that will not forget your previous knowledge. You, you incrementally added your knowledge for your model. So let's start from our first setting, the unsupervised domain adaptation, UDA. Here we also show the difference between generic domain adaptation and UDA domain adaptive person-read ID. We can see for generic domain adaptation, we can have same classes, but in very different, totally different styles, like art, clip art, product photo, and real world photo. So basically, you just want to transfer the knowledge of different styles into your target style. But for person-read ID, we have already seen, first of all, we work on very fine-grained classes. So you have to pay more attention to detailed information. And the second of all, we have non-overlapping classes. So which means in market and Duke, you have totally different identities. So you cannot reuse your classifier in this case. For UDA person-read ID, there are three major domain adaptation approaches, such as first, we can consider adversarial learning. So in this case, we can have a source domain, target domain. We train two different encoders or neural networks for each domain. And after that, we use a domain discriminator. Once your representation is close enough that can for your domain discriminator, we can say your model is robust enough to domain gap. And the second one is without this domain discriminator, we directly set some metric to measure the distance between source and the target domain distribution distance. And by minimizing the distance of a source domain, target domain, we try to have a similar representation distribution. So this approach is mainly called metric learning. And the third one is called pseudo-labeling. It's a method first used for semi-supervised learning, but recently a lot of people use this technique for unsupervised domain adaptation ReID. So the idea is very simple. You can use some clustering or some technique to assign pseudo-label for your unlabeled data. and then you retrain your network with these pseudo labels. After unsupervised domain adaptation, we also have a very recent approaches that is more related to fully unsupervised learning, or in this case, we can call it a self-supervised or contrastive learning. So for this more recent one, we can, for example, to achieve self-supervised learning, what we can do is when we have images or video, we can add some data augmentation, like as artificial perturbation to create a pseudo-positive pair. And then we try to maximize the representation similarity between your created positive pair. So by repeating this process on each images, your model representation can be invariant to this artificially added perturbations. But for inside this process, how to make it more suitable for unsupervised person reality, we can ask these two questions. By answering these two questions, we can make it more suitable for unsupervised person reality. So the first question is how to design better data augmentation. So from this level, so in our contribution 1, we use a GAN-based image level augmentation to replace very traditional data augmentation techniques. And in our contribution 3, we try to use the old domain encoder as a feature level augmentation to enhance the transferability between incrementally added data. And the second question is after data augmentation, when you have two augmented views, how to learn better invariance from these two augmented views. So in our contribution 2, we talk about a neighborhood relation aware losses. So this losses allows you to learn better invariance after data augmentation from this level. Okay, so we will first talk about our contribution 1, GCL joint generative and contrastive learning. So we have already seen for contrastive learning in person reality, previous method, they all use very traditional data augmentation like flipping, cropping, and erasing to bring in your artificial perturbations to create your positive pair. But the problem is all these processes are randomly applied to each region. So you cannot really control or you really know which part will be erased. So you may lose very critical identity information after your random data augmentation. So here example is basically the most important part is the color of her t-shirt. But in this case, in the photo, we will lose it. So what we can do to make our data augmentation more reliable and more controllable. So we argue that in one person image, all the identity feature can be categorized into two categories. First of all, we will have some ID related feature like the color distribution of this person's clothes and the body shape of this person. And we also have a lot of ID unrelated feature like the pose, viewpoint, illumination, camera style of this person image. Our motivation is to disentangle these two kind of features into two space, and we only modify the ID unrelated feature. And we want to keep as much as possible our ID related feature. So here we can, what we can do is we use again to generate an augmented view. We just change the pose or viewpoint of this person, and we use the generated images as an augmented view for contrastive learning. And here we have our general architecture of this method. So basically, our contribution is to propose a mutual promotion way for this person, unsupervised person ID. First of all, we have a generative module. So the generative module can provide better augmentation for our contrastive module. And then the contrastive module, because for the GAN-based generation, you also have to use some discriminator to tell you whether this image is realistic or not. So by using our contrastive module as a identity discriminator, we can increase the generative quality inside this process. So here, let's first say the generative module. In this module, we propose a mesh-guided person image generator. So the structure is mainly based on some well-known GAN paper, such like CycleGAN. So we can first extract the original mesh of this person, but by rotate this person mesh, we can recolor the color from this image onto the mesh, the grayscale mesh. We can get a new images which serve as augmented view. So here inside this generative module, we have we have an identity encoder, we have a structure encoder, which basically is a very ResNet 50, such like this. And we also have some example. Here we can rotate to different degrees of original angle, and we recolor the grayscale mesh into colored images, and we use the colored images as our augmented view. So after you get your generated image, what you can do is to use the original image and your generated image as a pseudo-positive inside your contrastive module. So we can, in this case, we can create three kind of positive pair. First of all, we have an original image. We also have a generated image. And by using, we can also try to found or try to mine a pseudo-positive. We use a memory bank here to store all these unlabeled data representations. So after that, we use clustering to tell you this image and another image can be categorized into a same cluster. In this case, we call it a pseudo-positive memory image here. So by using this clustering algorithm, we can build another positive pair. So after that, we use all the image that doesn't have been contained into a same cluster as negative images. So we design three losses to attract a positive pair while reposing negative pair. So after this process, we can achieve our, contrastive learning. And we also conduct some ablation study from quantitative aspect, also from a qualitative aspect. So here we compare our baseline. It's a previous unsupervised person-ready method. So when we add GAN, we can have this. When we don't use GAN, we use TDA, traditional data augmentation, we can have this. But by using both GAN and the contrastive module, we can have the best performance. So which validate the effectiveness of our mutual promotion framework. And then we can also say with our contrastive module as a more fine-grained identity discriminator, we can preserve better identity information and generate a more realistic image on the mesh. And then here are some comparison with state-of-the-art methods. In this case, we tested 3 different baselines. On each baseline, we can increase some ReID performance from our baseline. And here are just some of our results for this work. But if you are interested, we have a lot of more results in our paper. So here we also compared the generative quality. Basically, we can see here for our method, we can see the generated images is more realistic, and we can keep better body shape information with our proposed mesh-based generation. So we can see here, the previous method mainly use some 2D joint map or some very implicit way to introduce structure variance, but we use very explicit 3D mesh to keep the body shape information and make our image more realistic. And here we show also another image to show that pose information and color information can be disentangled, can be separated. So in the first image, we fix the pose, we fix the structure feature, and we only change the identity related feature. So we can see here we have from person 1, it's more similar to person 2 in this case. And person 2 is the same way. So here is we can have a conclusion for our GCL section. So first of all, we can say GAN-based augmentation is an effective substitute for traditional data augmentation inside contrastive learning. And then we can also say contrastive learning can serve as a more fine-grained identity discriminator, which can help us to generate better person image. Despite we get some good results with this method, you can see there are still a lot of limitations for this work. First of all, it really depends on the generative quality. So after generation, you may lose some detailed information on the generated views. So maybe use the more recent GAN, like stale GAN, big GAN. We can generate better quality or more with more detailed information. And the second problem is because our method is based on the mass rotation. So it's very hard to generate a realistic images when there exist inconstant patterns, like here as shown in the figure. When this guy has a backpack or carrying object, our gun or our framework can hardly recognize this is not part of the human body. So normally our network can only regard all this information into a whole body patterns. And the third problem is GAN-based augmentation can be hard to train and takes more training time. So in the next section, we go back to the traditional data augmentation to avoid the more training time. And we try to use other actual information that can be found from our original mini batch to serve as actual information and improve the performance for our contrastive learning. So here in the contribution 2, it's called ICE, inter-instance contrastive encoding. So here we mainly consider the inter-instance or neighborhood relationship inside the contrastive learning. And here we can see from our previous work, we can use a clustering algorithm to assign pseudo labels for data. And when we have one cluster, normally you should have some pseudo positives inside the one cluster. Maybe they are from different cameras, this sub-cluster. So when we have multiple pseudo positive, there's a traditional way to learn similarity is to use the cluster centroid, which is the average representation of all the cluster instance. And we can push all the instance to get closer to this centroid. And there are some other techniques. For example, from this triple AI paper, they argue maybe we can have more fine-grained or multiple centroid that calculate from different cameras. So by adding this camera proxy of prototype, we try to also minimize the distance between different subclusters. So, but we think there are still another problem. It's we have a lot of different instances. These instances, some of them can be closer, some of them can be further. So can we consider the inter-instance affinity or relationship as actual information inside our contrastive learning? So here, our proposed idea is we can, based on the proxy, like our previous showed method, we want to achieve both cluster level and instance level agreement. So here we can use 2 encoders, one online encoder, one momentum encoder. The momentum encoder is just the moving average weight of online encoder, which is more robust. And then we try to use a clustering algorithm to find the clusters, and we calculate the prototype from each cluster. Then we try to minimize the distance between this anchor image and the prototype. After that, we can also have instance agreement, which means you can have multiple pseudo positives inside your cluster. And our contribution are, first, we propose a method to better to select appropriate pseudo-positive for your contrastive loss. And then we use the consistency before and after data augmentation as some pseudo label to help you to get better representations. So here is our first contribution. It's called a hard instance contrastive loss. So the case is when we select one image as an anchor, we use inside one mini batch, we can have some pseudo positives. You can say P1, P2, P3 are the images from the same cluster. And we also have a lot of negative images, which are not from the same cluster. So if we have several pseudo positive, how to select the best one to contrast with your anchor? In this case, previous method, maybe you can just select the random one, but we think we can first measure the similarity between this anchor and each pseudo-positive, pseudo-negative. And then, since some of them can have the minimal similarity inside the mini batch, we call it hardest positive. It's the instance that have the least similarity with our anchor. So this point can be regarded as the furthest one. So since other like P1, P2 are already close enough, why not we just to push the furthest one to get closer to your anchor? So here we select this one as our pseudo-positive. And by contrasting this anchor representation with the hardest positive, we can get better performance for our contrastive learning. And then we can also use the consistency before and after data augmentation. First of all, our idea is if your model is robust enough, your representation similarity before data augmentation, like the first row, and after data augmentation should be the same. So at least should be close enough. So in this case, we recalculate the instance-wise similarity inside the mini batch, and we use this one as a pseudo label. And after we add some data augmentation or some perturbation, we recalculate the mini batch similarity. So, and after that, we use a chiral divergence to measure the distance between these two similarity distribution. And we push this P is the one after perturbation to get closer to this one, original one without data augmentation. We can make our make our model or representation have a more data augmentation consistency. So, okay, let's see some ablation study after this. First, we show this baseline is also from that I presented the AAA paper. I tested on 3 data sets, and by adding our hard instance contrastive loss, we can get some improvement. And by adding our soft instance consistence loss, we can get a further improvement. And by combining both, we can have the best performance. And also after that, we also draw some TSNE figure to show the distance or to show the compactness of each cluster. We randomly select 10 cluster from our market data set. And we can see, use our two losses, we can have a better cluster compactness and have a better separability between different clusters. And here are the final results of our proposed method. We tested on with two well-known baseline. One is from NIPS, one is from AAAI. And we compare these two. And on the three data set, we can always get some improvement. And we also compare with some previous supervised method. We can see our fully unsupervised ICE is already get very close the biggest data set, MSMT. So, okay, there is the conclusion for, okay, there is a conclusion for our second contribution ICE. First, we can see mining neighborhood relationship can improve unsupervised procedure ID. And we propose two losses. First one is a hard instance contrastive loss. Basically, we select the hardest positive from multiple pseudo positives. And this one can help us to reduce intra-class variance from hard samples. And second one, we measure the consistency before and after data augmentation to get more consistency. And even we can get really good result with our second contribution. There are still some problems inside this method. First of all, we can see it's very hard to tune your hyperparameters, because if you add more losses or you add more technical part on your consistency, you should use more hyperparameters, such as clustering threshold to distinguish, to decide which instance and other instance can be categorized together. So especially under unsupervised setting, it's very hard to tune for different sized data set. And the second one, we can see it's a very general limitation for all these domain adaptive personality method. We can say ICE or GCL, these two methods only focus on one target domain. But if we have multiple target domain, or we have incrementally added data set, what we can do. So to answer this question in our contribution 3, because this one is unfinished work, is under revision. So I will only talk about the main idea of this method. But if we have more time, we can have more discussion after that. So in this presentation, I try to propose another method called UCR, unsupervised contrastive rehearsal. We use a contrastive rehearsal to accumulate your knowledge from multiple data sets. So here we have our background or the problem for our single domain adaptation. So we can see most of previous methods only consider one target domain. So in this case, we have a market that can be unsupervised, adapted to Duke MTMC. So on the test domain, on the Duke MTMC, we can get a very good result, like maybe 70%. But the problem is after the unsupervised domain adaptation, we cannot go back to market data set, which means you will forget your source domain knowledge. And the second problem is you only transfer your knowledge to one target domain, but it's very hard to generalize to unseen data. So what can we do? Is we can use a lifelong or continuous domain adaptation. So here we can see we have incrementally added data. For example, we have a market data set, we have a COHK data set, we have MSMT data set. We use these three as incrementally added data, and we also, in reality, we can also have some unseen domain, like we can use other data sets like as unseen data. So the situation in the real world is new data can be recorded day by day or from a new installed camera. So in this case, your new installed camera can collect more different style data for you. So can we train a generalizable model with this incrementally added data, but without forgetting your previous knowledge? The answer is yes. So for our lifelong domain adaptation, there are two challenges. First is how to avoid catastrophic forgetting on previous or source domain. And then you can imagine, because for unsupervised domain adaptation, our objective is to have minimal supervision as possible for your model. But if you have more data or more domain data, the annotation problem can be more arduous for your lifelong adaptation process. So we propose to unsupervise the contrastive rehearsal for our lifelong domain adaptation. So here, this is just the main idea. I will stop at this for this work. Here is the main idea of this method. So we can see, we compare, this is a traditional contrastive learning. So we build a positive pair with the, you can see some data augmented views or some pseudo positives from your clustering. So we use the encoder from the same domain to have this contrastive condition. So we expect that your pseudo positive can always be similar, more similar to your pseudo negative. But for lifelong or for continuous adaptation, what we can change is we can use the encoder from the old domain as an extra augmentation inside your contrastive learning. So here we just change, we add more perturbation or we add more augmentation for your contrastive learning. We can have your anchor, the similarity between anchor and the pseudo positive, but the pseudo positive is encoded with your old domain knowledge. And we expect the same condition. We can always have the most similarity for pseudo positive pair. And yeah, due to time constraint, I will stop my presentation for this method here. But if anyone is interested, I have made appendix after the conclusion. So just let me know. So I will first give the conclusion for this UCR method. We can see lifelong adaptation can help us to achieve general reliability from incrementally added data. So in this case, you can accumulate multiple domain knowledge one by one. And then we can see by jointly rehearsing some old sample and training new samples, we can try to avoid the catastrophic forgetting problem. And we also think there are still some limitation for our proposed method. First one is you can imagine for different days, some day you may collect more data and some day you may collect less data. In this case, it's very hard to balance the domain knowledge from different sized data set, because some data set may contain more diversified samples. So you should pay more attention to this kind of data. And the second question is, our method is based on rehearsal, which basically means you have to store some old samples in a memory or in a long-term memory. So maybe it will pose some problems for your hardware. Okay, let's give a final conclusion for my presentation. Okay, first, there's a summary for my 3 contributions. We can see from contribution 1, we try to improve contrastive-based person ID with GAN-based data augmentation. And the second contribution, we try to improve contrastive-based person ID use by using inter-instance relationship. So it's after data augmentation. And the third contribution, we try to achieve general reliability on multiple data sets, also on unseen data sets from incrementally added unlabeled data by cross-domain contrastive rehearsal. So here comes my conclusion for this presentation. So we can see for recent unsupervised person ID method, we can get very good results. We can get a remarkable performance that is even close to supervised method on medium scale scenarios, such as a market data set. There are 6 cameras, 1,500 persons. But if you want to make your person ready algorithm more reliable, so what we can still unsolved question is first, all these methods are very dependent on pseudo labels. So the quality of your pseudo label can be easily affected by clustering hyperparameters and your representation quality. And we can say also the traditional UDA or domain adaptation method can hardly generalize to multiple scenes simultaneously. And for our future work, so in short term, we can, because it's already a lot of people working on this. So to mitigate the pseudo label noise from representation level, so maybe before your domain adaptation or before all your process, you can think about to pre-train your model on large scale pre-training maybe a bigger data set, or maybe with more recent backbone networks like transformer to improve your representation quality. And the second one is more for long-term research. To get more generalizable representation, maybe we can go deeper into lifelong learning. So our method, our proposed method is based on how to say long-term memory sample rehearsal. So maybe we can think about to some cross-site selection method, or how to select representative images from each data set. And you, in this case, you don't have to store a lot of images, but you just store the representative images. And for data, the second problem is maybe we can think about from our data set aspect. We can think about maybe data-centric machine learning. So maybe before design algorithm, we first try to understand the importance of each data set. Maybe it's better to have an unsupervised evaluation for evaluate the diversity or some reliability of your data set before you design your algorithm and before being accumulated to your model. So yeah, that's our future work for short term and long term. So okay, so here are some publication list for my during all this PhD period. Okay, and thank you.
Okay, sorry, I was muted. So thank you, Chen, for your presentation. I don't know where I can see you. Okay, I can see you here. And thank you for staying in the 45 minutes range. Now we are entering the second step of this defense, during which you will have to answer the questions from the jury.
Yes.
And so I'm going to give the floor to the members so they can ask questions. And I suggest the following order: Vittorio first, then Xiliang, your two reviewers, then Rémi, then myself, and to conclude, François and Benoit, your advisors.
Okay.
So Vittorio, if you are ready, please, you have the floor.
Yes, thank you, Frederick. Thank you also for the kind introduction. And first of all, thanks, Chen. It was a very nice presentation, clear.
Thank you.
And also thanks for your work, which is much more of what you presented. Your thesis as it is something also missing, which is the last work about lifelong learning was not present in your thesis. So
yeah,
thanks for sharing some ideas. Frederick, I can ask as many questions as I like, or I don't want to in a way take the floor for.
Well, usually in France there is only one round, because in some countries I know that it's one question per person and then several rounds. In France it's usually one round. There is no limit, but I mean, try to be reasonable.
I take okay, guys, take a rest. I have a couple of hours of questions. No. Okay, so the first, I would like to ask, first of all, what do you mean in your conclusions? Starting from the end, going back to the start of your presentation. So you mentioned in your conclusions that you cannot deal with multiple scenes. I didn't get it. What do you mean exactly for not dealing with multiple scenes?
Okay, can I go back to my slides?
Yeah, please. Can you share the slides, because I have some pointers. It's better to share again the slides.
Okay, maybe I like this.
Here, the next one. The next, exactly. Can I generalize to multiple scenes simultaneously? What do you mean for multiple scenes?
Oh, it's mainly related to the domain generalizability.
Okay, so multiple domains.
So multiple domains, yes.
Okay, so not multiple scenes. Okay, just there was a punctual, yeah. And you mentioned a couple of times the issues, and thanks for also raising the good point and the bad points. This is nice, because not many people is addressing also the weak points of their methods. And you mentioned about a couple of points about these clustering issues, about these hyperparameters linked to the clusterings. And I agree with you in the sense that many works in the literature are say, okay, I make some pseudo labeling, and it seems that the clustering always works very fine from the start to the end. But in my experience, this is not true. And I'd like you can in a way elaborate a little bit more on this. So for example, in your cases, when you make your clustering or make your pseudo labeling, how do you manage these issues?
We just, yeah, because for our research, we cannot really measure the, how to say, the separate performance on different data sets. So what we did is we just fine tune our parameter in the supervised condition on one data set, let's say, for example, market, and keep all these hyperparameters same for other two data sets, for example, Duke and MSMT. And when we can get always the best performance, the better performance than previous method, normally we can see our method is better.
So you in a way perform the sort of grid search of the parameters on the basis of your
yes.
results.
Mm-hmm.
Okay. This is not exactly in a way fair. Let's say.
Yeah, I'd like to say, yeah, you used some labels to train these hyperparameters.
Okay. Mm-hmm. Okay, so another question was about the contribution number 2 about the contrastive plus consistency method, and this was an interesting work. I'd like to ask, even in this case, some for the consistency part.
Yes.
You in a way compare using KL divergence all the behavior of a distribution, right? This is exactly the label. All the consistency between the two distributions in the mini batch, right?
Yes, it's inside the mini batch.
Okay. Because what you want is to, in a way, reach, in any case, a similarity between the two distributions.
Yes, exactly.
That's the point. So the question is if you can discuss why you make this choice instead of making, for example, to, in a way, maybe to select some of the most hard positive and hard negatives in your mini batch and try to make it, let's say, not simpler, but in a way focus more on the anchor and hard negatives that are positives, like in a triplet, for example.
So it's mainly the question about how to select pseudo positives, negatives.
So no, the question was what you show here in the bar plot was all the samples in the mini batch.
Yes.
Right? Yeah. Yes. And you make this comparison. So what you want is to make the similarity between P and Q, which are the two distribution before and after data augmentation.
Yes, yes.
Okay.
We want to enhance this consistency between.
Yeah, my question is, instead of calculating the similarity before and after, why you didn't select some of the samples linked to the anchor before and after? Instead of using the entire distribution, the mini batch, why you didn't use some selected samples? Because what I expected that this similarity is fine because you compare the entire distribution, let's say, but I don't know which is the contribution of some samples with respect to the others. So what I expect is actually that there are some samples which are more contributing than others in this consistency. I don't know if you got my question.
I got it. Yeah. From my understanding, it's mainly about why not first select some more hard positives and hard negatives.
Yeah.
So yeah, that is a good question. Actually, we didn't test it, but for this method, we only consider maybe we can just calculate the similarity between each instance pair in a mini batch, so that we can have how to say a global relationship for this mini batch. And for maybe we can test it. Maybe first select some hardest positive negatives and then do this consistency.
Okay. Thanks. Another question was about the contribution number 1. Okay, you stressed about the fact that you disentangle the structure with respect to the ID information. Here I have actually a couple of questions. The first one is about this disentanglement. When you say disentanglement, you assume that the information about ID and the information about structure is known, right?
Yes.
So it's what about if you don't know, especially if you don't know, so you know the label and it's fine, but what characterizes the label in terms of structure and IDs, it's less clear to me.
First of all, I'd like to say we are working on pseudo identities.
Mm-hmm.
So using some clustering. And after that, because our objective is try to have some representation, identity representation that irrelevant to some pose or viewpoint variance. So in this case, that's why in our paper we said it's best to first pre-train or to warm up our identity encoder with existing unsupervised person ID method, and then we can have a better disentanglement quality. And after that, we use ResNet 50 is a very traditional encoder for to extract identity features, and we use some very simple structure encoder for our meshes. And by using some circle GAN to reconstruct in different views, we try to disentangle these two kind of features.
Okay. Okay, thank you. The other questions and last question maybe is about this method. I think I made also this comment on my report. Was about if you go back one slide, back again. No, it's something you go on, go forward. It is the first no, forward, go 16, go to slide 16, 17. Yeah, this one, exactly. No, yeah, this one.
Okay.
Yeah, I found, I didn't get clearly why you need all this generation module, because you start from the original image, you have a couple of, you have the pose, original pose and the new pose, and then you generate a lot of stuff and compare, discriminate. Can you, in a way, summarize the rationale behind this, all this generation discriminator module? Because I don't understand actually why you generate a couple of times your, right, you regenerate a couple of times, right? Because x prime, x second, x two primes are in a way regeneration, right?
The initial idea is from a GAN paper. It's called CycleGAN. So in CycleGAN, we try to first use this one to reconstruct your feature, which can help you to train your generator identity encoder structure encoder. And after that, we use the identity feature from the new structure image and recalculate one time. It's called cycle, how to say, cycle consistency.
Okay. You go back to calculate if, yeah, okay.
Yeah, because we want to use this, the identity feature from the new structure and go back to your original structure. That can further help you to disentangle two kind of features.
Okay, I got it. Thanks. Yeah, now it's a bit more clear. Okay, nice. I think to me, for the moment, this is what I would like to ask you. And there are some comments also for the last work about lifelong learning, but yeah, actually you just presented a slide and the idea was fine. My only comment is that yeah, essentially lifelong, if you have to store previous data to maintain in memory, to in a way not to forget the source, it's yeah, it's a classical approach, let's say. In the state of the art works are mainly also storing, and how which sample to store, it's not easy to find. This work to me resembles a little bit something related to domain generalization, in the sense that you don't know your target. You have okay, a lot of additional data, incremental data, you can get it, and how to maintain the same performance for the new and the old data. Maybe you need to, in a way, rearrange also the data because we don't have in error identification data sets which are able to demonstrate that a lifelong RAID problem can be in a way fixed or tackled. And yeah, my last comment is that I just discovered that also another data set was retired by the scientific community. First, Duke was no more usable for getting some results, and now also MSMT, right?
Yes.
So my comment is that so it's difficult now to sell other RAID method for which we can't compare with MSMT and Duke. We have only market, let's say we have the oldest one, which are the CUHK and the Viper and whatever, but recent papers are anyway comparing with
yes.
with Duke and MSMT typically, and now they cannot be used anymore. Anyway, that's life.
Yeah, but yeah, this question is only for Duke. For MSMT, it's still usable.
No. Okay. My student told me that also MSMT was retired. So please check it because please check
you
it.
can ask Professor John. It's from
yeah, actually, MSMT is released by our group.
Okay, good. It is still there or not? Because my student told me that was retired, isn't it?
Yeah, it is still available, but you need to send an email to me, and I will send the agreement to you. You just need to sign this agreement and send the scanned copy to me.
Okay, but before was free. Before was fully.
Yeah, it's totally free. Yeah, we just need this agreement to protect some privacy protection. Yeah.
Okay. So yeah. Because I will check with my student because I received this wrong information, and but I like to know that it's still usable.
Yeah. Just send the email to me.
Yeah. Okay. Perfect. Thank you, Xiliang. Thank you very much.
No problem.
Okay, I'm fine. I finished. Please, thank you again, Hao Chen, and yeah.
Okay, thank you, Vittorio. Feel free to come in later if you wish. And now we are moving to Xiliang. So please, you have the floor to ask questions.
Yeah, thanks, Jury. Thanks for the kind introduction. Hao, thanks for your clear presentation. I have read your thesis, so I know your work well. Well, I just have some questions. The first one actually is an open question. So, lots of papers claim they have got a very good person reality performance, right? But the person reality algorithm is still not ready for real applications. So on page 6 of your slides, can you go to that page? So you list many issues in person reality.
Yes.
So among those issues, I think is page 6.
Is this one?
No, page 6. Yeah, this one. So you list lots of issues. So
yes.
Among those issues, which one do you think is the most challenging one?
I'd like to say, for me, it's the domain gap.
The domain gap? Okay.
Yeah, because it's domain gap is combined by a lot of factors. Because in different domain, maybe you can have different resolution, different illumination conditions, or different viewpoint. So for me, domain gap is you have to consider a lot of challenges in the same time for different data sets. And
okay.
Yeah, that's my understanding.
Okay. Actually, you also mentioned in your first work, you also mentioned that if you want to generate augmented images with very large viewpoint differences, that will be very difficult.
Yes, exactly.
So yeah, I agree with you. I think the viewpoint change is another very challenging issue. So do you have any ideas about how to address this issue? So if we have a very large viewpoint change, and how to address it?
So you mainly want to talk about the how to say, we go from front view to back view, or we also from we talk about maybe, let's say, top view.
Yes. So from for example, the front view to back view. From the back view, this person is wearing a backpack, right? But the front view, there's no backpack, so the appearance would be very different.
So yeah, I have already thought about this question. For me, it's maybe because we just use some very traditional math generator inside our algorithm. But we may expect there's a more and more better mesh generator. So I have seen a paper in recent paper, they try to distinguish first, there's a human body or carrying object, or maybe you can have some interaction between human and the object. And then you only try to extract the feature from that human body part. And then, yeah, maybe it's something related to human parsing, or maybe it's from some human object interaction mesh generator.
Okay. I think that could be a possible solution, but I think that's a really challenging issue for personal reality.
Yeah, also.
So similar to the close change issue, right?
Yes.
Okay. For your first work, I think it's a very good idea to decouple the features into different types, right? And you also use the 3D body model to generate augmented images.
Mm-hmm.
So that means you can generate augmented images with any viewpoint, right?
That's also, yeah, for some viewpoint, yeah, it's a very, maybe have a low quality.
Yeah, so that means so then I think that will be a very important parameter. That means you need to decide the proper number of augmented images and the proper viewpoint.
Yes.
So how you decide the number and the viewpoint of your augmented images?
For this work, we just use I think it's one of a simplest solution. We just fix all this rotation angle to every 45 degree, and we randomly select one as our pseudo-positive pair. But yeah, I think because this is a random selection from this 7 possibilities. So in some cases, you will have some small angles like this one or this one. But I think the hardest generation is you totally change from back view to front view, let's say 180 degrees. So by random selection, I think you will have at the end, you will have averaged let's say pairs composed of simple one and a hard one.
Okay, actually, I think different viewpoints correspond to different quality, right?
Yes.
So maybe the 45 degree has a better quality than the 180 degree.
Yes, that is also, we measured the FID. It's the generative quality from the GAN part. We found that for 45 degree, for small angle, you have a better generation quality. And in the middle, for very big degree, you have a worse quality.
So your algorithm do not have the mechanism to select higher quality images, right? So you just randomly select those images.
Yes.
Okay, I see. Another question is in your second work.
Okay.
So you just assume that in each mini batch for each anchor image, it will have some positive samples, right?
Yes.
But I think because in each mini batch, it only have a very small number of images. So maybe for some anchor images, it do not have positive samples.
Yeah, because this is mainly related to different clustering algorithm. For that one, we use this, it's called DBS CAN. So basically, it's based on, we have to set a minimum cluster numbers for a cluster. So we set 4. So in this case, at least have 4 pseudo positives.
Okay.
for each
I see.
cluster.
I see.
But
I
if
see.
you
Okay.
use different clustering, like key
Mhm.
means, maybe you just have one or two.
Okay, I see. I see. It's clear now. Okay. For your third work, so I think it's a very good work. It's very interesting, and actually we are also working on similar idea. So I think your performance upper bound should be you just mix different datasets together as a uniform one, and you directly train on this uniform dataset, right?
Yes, our framework is first we can say, let's say this one. So for example, we use 3 incrementally added data sets.
Okay.
We first train on market, and after training, we just use a long time memory, and we store 2 images per identity, per pseudo identity inside this memory, and this stored old image will be trained together with the second COHK one.
Oh, I see. So after training on markets, then you train on COHK and market together.
Yeah, some sample from market and COHK as a
okay. Well, another, I think it's a more reasonable setting might be after you training on markets, and then you train on COHK, and then you should assume that the market images is no longer available for training.
Yes, this is yeah, because I have gone through some lifelong learning math paper. They have a different setting. For this one is they always call this for replay, recall, or rehearsal. So basically, the idea is to store some images from a previous setting and into a long-term memory, and then you can use it again. But what you mentioned is maybe more, how to say, a challenging one, but have more real-world values because you don't have to rely on old domain images. So you have less hardware constraint.
Maybe you just need to store features, not the original images, right?
Yeah.
Just store features in your memory bank.
Yeah. There are some paper maybe storing images. Also, some paper I see they can store features. Also, some papers they try to train a GAN. Inside the GAN, they depends on your setting. When you enter into the second domain, you can use the GAN trained from first domain to generate some images. Yeah. Replace the stored images.
So just curious that how many images, for example, from markets you need to preserve for the next step training?
Because for our method, we can, because I used this one is for the third method. So here we used both image memory and a feature memory.
Oh, I see.
Yeah, because to have the best performance.
Okay.
Inside our method, we store 2 images per pseudo identity from previous. I think it's acceptable size.
I see. Okay. Thanks.
Thank you.
Yeah, that's all my questions. Thanks.
Okay, thank you for your question.
Okay, thank you very much. Now we are moving to Rémi. If you have questions, it's your turn now.
Yeah, thank you, Frederic. Thanks, Hao, for the very nice and clear presentation. So first, I would like to say that I'm very novice in this topic in person identification, also in general in vision. So apologize if my questions are a little bit naive. But first, I would like to get of the space of domains where you made the contribution. And so I'd like to try to clarify for myself exactly where you've made those contributions. So what I understood was that the goal is to do this personal identification, which I understood is a classification problem where you have an image and a set of other images and trying to find which one among the others, is corresponds to the identity of the person in the first image. Okay, and that is the goal, right, of your work, is to try to improve on this task. Is that correct?
Yes, correct.
Okay, and in order to make improvement there, you've worked on self-supervised learning methods that are based on contrastive methods, basically, and you have made contributions in. So those contrastive methods are using two elements. One is data augmentation, which is like random transformation of the image that should preserve some property, obviously. And the other is some kind of a metric to compare the images.
Yes,
to
after
learn
the
this imbalance. Okay. So the first. So I understand that your first contribution was to design data augmentations, right? Instead of using already existing data augmentations like cropping the image or things like that, you want to learn some data augmentations. And the way you want to do that is by using some kind of 3D model based on a mesh of a body. So my first question is it some already existing software that returns a mesh given an image of a body?
Yes, there are a lot of people working on mesh generation. So
Okay.
I just use existing work as our backbone and try to extract a mesh from their existing model.
Okay, and so now you've got a mesh, and then you make rotations. I understand that. So your transformations are rotations only. But since you have the mesh, you could think of maybe other transformations, like transformation of the body itself, like the shape of the body. If the person is walking, you can think of different transformations, and maybe some people have already worked on that. I mean, other people maybe have worked on transformation of the mesh that would correspond to different poses of the same body.
Yes.
That you could use as well, as model for generating like corresponding images with the same person with a different pose. Do you think it would be possible?
Actually, yeah, it's possible. You just try to, after you estimate a corresponding mesh for one person, for our work, we just try to rotate this mesh to simulate the different viewpoint of different cameras. But yeah, exactly. Actually, you can try to modify your mesh because it's just related to person pose. Yeah. Yeah, you can do both, I think.
Because then you would generate images of the same person with a different pose, and that might be like quite useful because that's the kind of feature that that would be useful to in your identification to be able to learn features that are independent to the pose, right?
Yes.
Of the person. Because here you are presenting, you are learning features that are independent to the angle, to the viewpoint somehow, but not to the pose, right? So if you were able to use this, okay.
Yeah, maybe that can be considered as our future work. Yeah.
I see. No, maybe like to go back to like the contribution. No, I have a question. Is all of this is basically to learn a representation of an image? Is that correct? All this work is about learning a better feature, a better encoder of the image. Is this correct?
Yes. I'd like to say all these three contributions is based on self-supervised learning.
Okay.
So we just try to either modify data augmentation or try to modify loss function to make it more suitable for person ID. And basically, yeah, this question, this self-supervised learning or contrastive learning is try to learn unsupervised representation by using this process. So yeah, it's for representation learning.
And once you have this representation, what do you do with them? You just check the similarity between the representation of the first image and the representation of all the other example images, and then you check to take the one which is closest. Is that the algorithm in the end?
Yes, this is our objective for person ID. So, for example, after we learn this representation, we can build a representation for each image inside your data set. And when you want to find your target one, so you just measure the similarity score between your query and each of the samples in your gallery. And the topest score gives you maybe the simulated one.
Okay, all right. Okay, so you just learned an embedding of the representation of an image.
Yeah.
And so at some point in the conclusion, you mentioned that you have improved over like previous unsupervised learning methods for re-identification, and you were close to supervised methods. So I was wondering, what does it mean to use supervised learning methods here?
Maybe it's related to this one, this setting, unsupervised domain adaptation. We can start from a labeled source domain. We try to first pre-train our model on because you can imagine in the real world, because we can collect some data at the beginning, because we want to have a warmed up state for your model. And then when it deployed to different user or client, so your user or your client cannot re-annotate their data set because of you cannot expect all your clients to have enough human resource to do this annotation. So what we can do is first use the knowledge that pre-trained from your very beginning data and use their unlabeled data to transfer your model and to adapt to their use case.
Okay, so you already pre-trained something based on label data on some subset, some domain, but then you want to use this. The representation has been learned by that, and then keep learning by using unlabeled data of corresponding to the new domain.
Yes. Yes.
Okay, and then in the end, do you want to for example, let's say you say, maybe we don't have so many labeled data, but maybe you have some data, but you don't have so many. So would you say that, for example, these self-supervised methods would be useful here as well, where you do this pre-training with self-supervised learning and then do some kind of fine-tuning with a small number of labeled data? Mm-hmm. In the end, have you looked into that, or it's something we can
yeah, that's also another setting, because yeah, for this self-supervised learning, basically it's designed for pre-training your model from some big data set, yeah, as a good starting point. And then maybe it depends on your use case, because you can think about some cases you can have annotation, but some cases you don't have annotation at all. If you can have annotation, just use the very traditional transfer learning with annotation to your use case. But if you don't have annotation in your target domain, you can think about to do unsupervised domain adaptation. Yeah, it's mainly based on the use case.
Okay. All right. Going back to the first, it's going to be probably my last question. Going back to the first, your first contribution about learning this data augmentation. Do you think there would be a possible way to learn this data augmentation, this transformation of the image automatically?
Yeah, I think there's a way to.
Without having to use this pose, this body, the shape representation by this mesh and so on, to do it completely automatically. Try to find maybe adversarially what are the transformations that preserve some important features that you want to that preserve the identity. They learn maybe using some data, some label data, learn these transformations using some label data, and then those transformations would be used even in data set where you don't have label information.
Yeah, I'd like to say it's a good question because I have already seen some people, they don't use GAN, but they try to automate the process of selection from this existing data augmentation with with NAS. It's called neural architecture selection or something. Search. Yeah, with this method, maybe some people use this method to automatically select the different operations in the backbone to build your backbone network. But I have already seen some people from I think from Google Brain. They used this method to select good data augmentation combination from all the existing data augmentation methods. And maybe just use some labeled data as a validation set and try to have the best performance on the validation set. And then you fix that automatically selected data augmentation site for your other data.
Okay, maybe just the final question. I need to ask you this question. Do you think we could use other self-supervised learning methods that are not contrastive? For example, the bio, something I've been working on last year, the bootstrap your own latent. It's a method, it's a self-supervised learning method, but that doesn't use any contrastive loss.
Yeah, exactly. Yeah, it's a very good direction for future research, I think. Because I have already seen some people try to use reconstruction instead of this data augmentation contraster. Maybe to learn better representation, or maybe I also see some people use some other techniques, all these techniques, reconstruction or I don't know, for self-supervised learning. But yeah, it's a very good research direction for future work.
Okay, thank you very much. I'm done with my questions. Thanks.
Thank you.
Thank you, Remy. So before giving the floor to your advisors, I would like to perhaps ask myself a couple of questions. The first one is related to the use of synthetic data. So you made one step into this direction by generating, augmenting the data with generated data. And so we could imagine that the next step could be to use purely synthetic data, because in this case you would be able to control everything, and then to make the pairs you want, to make the data set as diverse as you wish, change all the parameters, the illumination, domain gap, whatever you want. And I think that there are data sets, I don't remember if you use them, such as the name is the synthetic person re-identification data set. I don't remember the name, but I know that there is already one data set. I don't know if you use it or not, I don't remember. So from your perspective, what would be the advantage of introducing purely synthetic data in the training process?
That's also a very good research direction. Actually, because I have to say for this real world data, especially related to video surveillance, you may always raise some concerns about privacy protection. So when you can design all synthetic data set, first of all, it's a more, you can train your model, but without any real world identities. So a second one is you can use this. I have seen some papers that use a game engine to design how to say fully virtual identities and put this identity or persons into different scenarios. And you can imagine, because for collecting a real world data set, you have all, it's very hard and time consuming and very hard to cover all the, let's say, weather condition, etc., different situations. But with a virtual data set, you can always use your game engine to simulate different, maybe raining day, or cloudy day, sunny day, without any real world annotation process.
Yeah, so but why don't you use synthetic data in this case?
Yeah, I can say, yeah, because the main approach is still compare with the real world data set, because in the end we want to it workable on the real world data set. So maybe we can first pre-train our model on the synthetic data set and then transfer to real world.
Yeah,
so,
in the back,
my experience,
in the back et al. Paper in 2018, they use the synthetic data set to pre-train or whatever, and then they apply the model on real data. So it's possible to
I think so. Yeah.
To address real data with synthetic data.
Yeah.
Okay. Okay. Yeah, there's something also that I would like to have your opinion on. In fact, when you present your results, and it's mainly because it's what people are asked to do to have accepted paper. You provide comparisons with rated work. Then you have your plus X%. And you say, yes, so I'm better than previous approach, so I'm happy, and then my paper is accepted. But at the end, what I would like to know is, do you think that we have reached the limits of what we can do? Because this problem is ill-posed in the sense that even for human beings, it's probably not possible to have 100%. So, and I don't think that in your manuscript, neither in your presentation, you give any example of failure cases, and you do not analyze these failures. So, what is your opinion on this? When your algorithms fails, do you think that they are really, they can fail on very simple cases, or are the images so difficult that even for human beings, it's quite impossible to find who is represented?
Actually, yeah. We have some failure cases comparison in our papers, but here in the presentation, I only show general limitation of each paper. We have already compared with our method with previous method on the failure cases, and we can see, because we have already have a very good result on some data set, let's say market, this one. So actually I have visualized some failure cases that are still existing in our algorithm. We can see it's a very detailed difference between your query and the gallery. So they could have maybe two person, maybe they just wear very similar uniform.
But it's on market, it's the easiest one. So
yeah.
on more difficult data set, is it the same? Or do you think there is a margin for progression?
For the, yeah, it's for the hardest data set and for MSMT, this one. I like to say even for supervised method, there are still a lot of space for improving, because we just reach MAP at around 50%. So yeah, actually we have a lot of space for MSMT, and we already I also see some more recent papers, they propose even bigger data set than MSMT. I think we should consider that. Yeah, maybe later.
And so from your experience, what are the most difficult cases for your method? When does it fail? In which cases? And how could you explain, or is there any typical cases for failure?
For failure cases, yeah, most difficult. Yeah, it's I think it's just like what I said. Maybe for market, for example, you have two people wearing very similar uniform. They're working in the restaurant. Maybe they are in the same how to say market, supermarket. So when you have very similar clothes, so you can be very easy to fail on this case. And when you have a very different poses or viewpoint, maybe you can also fail.
Okay, maybe one last question. It's a general question. So in the domain re-identification, in the question related to person re-identification, the progress, they are due to some general progress in visual representation, or more generally in computer vision. And there are some specific component or some specific algorithm or representations for this task. So how would you characterize what is specific to person re-identification versus general computer vision problems or other fine-grained classification problems?
Because here for person re-ID we have first defined it as a fine-grained image retrieval task. So
but you have for instance some birds classification problems. So to which extent is it different?
yeah, for other fine-grained classification task, we can say it's it's a similar. But yeah, you still have to pay attention to this human pose or very different viewpoint, because it's in the video surveillance scenario. A lot of other data set it's just images. Like here is just I don't know which kind of camera they are using. So first of all, it's a fun, yeah. Technically, I see person real ID is inside this task. You have to simultaneously consider multiple questions. So first of all, it's a fine-grained. Second of all, you may have imbalanced samples for different identities. For some, I have already analysis market. I saw from some identities, they have maybe 2 or 3 images. For some identities, they have more than 100 images. So imbalance is another problem. And I think that's why we always use this how to say, sample selection inside our person real ID. Yeah, that's another question for imbalance. And maybe we have also, in the case, if you just have 2 or 3 images, then this task is also related to few short learning. For our method to build a centroid for each cluster, this one, to build a centroid for each cluster. Actually, this is the first idea that used in few short learning community, and we borrowed it into our unsupervised person real ID. So this task can be related to a lot of different tasks.
Okay, thank you for your answers. And now to conclude this Q&A session, we'll let François and Benoit, I don't know in which order you would like to talk, to maybe give some comments or even ask questions. François first, maybe?
Yeah, I'm starting. I'm just going there because it's simpler, so we don't have to deal with the microphones and that. So make it simple. Don't destroy. It's working, so that's right. So I don't have special question for Ao, but just to thank Sim, because this is a very nice topic that I like, but this is very hard, in fact. So why I like this topic, because it's a general basic topic in computer vision. So how can we characterize one object independently of the illumination, the viewing angles, occlusion, and so on, all the art challenges that we have. And so it's ready to characterize this visual representation. So it's a very nice, and it's a hot topic because many people have tried to work on it. And as Frederick say, you know, it's similar to many tasks, but I think it's here you have you combine all the it's not just, you know, fine grain, it's very, very fine one entity, and also with real world, so with a very bad quality acquisition, and still to be able to say, is this the same person? And so that's why it's very challenging. And on top of that, when we try to look at the different data sets, so there's a lot of bias. So Ao didn't show all he has done, but he has done more than what he writes in his manuscript and so on. At the beginning, we are also trying to see what are the semantics, you know, the attributes, but it's hard to get a good result. And also we try also the illumination, you know, because illumination is a key thing. And so as Remy said, that we can change the viewpoint, we can change the pose. So he has tried to change the pose also. I don't want to say it, but he has tried. It's hard. And not just just the pose, but also the illumination to make it darker and so on. And that's we didn't succeed nicely. And the prime of this data set, you know, this small data set like Market and Duke, you know, usually they have few cameras who are close to each other, so they have the same illumination. So it's let's say easier to start boosting your algorithm and to have a good representation. What I understood from MSMT, I didn't look at the data set, but it's more diverse. So you have more cameras with more illumination, and it makes also more difficult. So there is some bias hidden behind the data that we don't see. But that makes the challenge very real. And for that, also, I want to thank ESC, the company behind that, tried to didn't give too much problems, too much constraint, and they give us some freedom. But also we try and ours try hard to make it realistic and usable in the real world. So as we say, I'm not sure that it's still yet usable. Not far, but there's still some. I think there's still some work to do on that part. And so with all these constraints, all these difficulties, our as always stay calm, very involved, read a lot, state of the art, and sometimes get very not frustrated, but like doesn't know where to go because lots of things has already been done, and to get a better result, it needs lots of fine tuning and spend lots of time to tune these parameters.
So very competitive topic.
Very competitive, but you never give it up. So up to the end, and you always find a way to make it work. So that's very nice. So congratulations to be able to don't give it up in this hard topic. So that was my main point. So thanks everybody for
Thank
being.
You, François.
So,
Benoit,
one
comment or questions?
Thank you for your question. It was thank you for your presentation. Like François said, it's still a challenging issue. This topic of re-identification. We are not too far to this result will be maybe exploitable in the industrial product, but just a few questions. Maybe to take care of video many frame of a tracklet could be a solution to. Do you think it will improve the results? Like Lancer, maybe.
Yes, we can use the temporary information to further improve it. Yeah.
Thank you.
Thank you.
And I congratulate you and François' team for this work.
Thank you, Benoit. So we are done now with this Q&A session. It's good to see that you are still alive, so we can continue. Most of the work is done for you. So now we are going to deliberate. As far as I understand, Benoit is not going to join us because he's not. He's an invited member. However, François will join us as the advisor. So I don't know, technically speaking, I guess you have to maybe empty the room, or is François going somewhere else?
I have to stop the YouTube.